Welcome back to the second lesson of Cornell compilers. Before we get started with the second lesson, we're going to do our Anki cards from the previous session. It's been a couple of days since I've done this, so probably not going to remember much of these. Okay, what does semantics mean? From memory, that was the language correctness according to some spec or some definition of the language. Sweet. So that was fairly easy. So I'll click easy and we'll see it again in 4 days. What is lexical analysis? So lexical analysis is the first step in the compilation, first step in compiling, and it's basically where you take an input stream, which is your source file, and you convert that into a list of tokens. Yep, fairly easy. What is syntactic analysis? Syntactic analysis is the I'm guessing it's the second step in compiling. It's where you take your tokens and then you convert them into an abstract syntax tree, which basically shows you the operations and the operands that are operated on in the form of a tree that you can follow in some sort of traversal order. Let's token stream list into an abstract syntax tree. Yep. Compilers. What is semantic analysis? So yeah, this is the next step, the third step in compiling. That's where you... let me think. That's where you take the abstract syntax tree and you do you take the abstract syntax tree and you do that's right, you do type checking on it, and you do something else. I don't 100% remember. Oh right, yeah, you it's in the name. You check it for semantic correctness. Yeah, you make sure it's a semantically valid program. Type checking checks the correctness of the program. I'm going to say good because that wasn't that easy. What is code generation? So that's the fourth step in compiling, and it's essentially taking the semantic or the result of the semantic analysis and then converting it to an intermediate representation, which can look like the three operand pattern. I don't remember much more than that. That's right. The control, it creates a control flow graph. That's right. Yep. Can also create some other intermediate representation, but yeah. Cool. Okay, we'll do that again. Compilers. What are some basic ways the compiler optimizes code? The first and most important thing was register allocation, figuring out or representing your variables and assigning them to specific registers to get the most out of the program. I can't remember the second thing I wrote down. That's okay. We'll see what it was. So register allocation, assigning variables to hardware registers, and using more efficient CPU instructions to eliminate the need for branching. Yeah, cool. So some architectures may have more advanced CPU instructions, and you can do a lot more operations with a lot less computing power. So I'll do that again. Using more efficient CPU instructions to eliminate the need for branching. What is meant by the front end of a compiler? So that's basically anything that's not machine dependent. So anything or anything that has nothing to do with the architecture of the machine that you're on. So the semantic analysis, syntactic analysis, lexical analysis, intermediate code representation. Yeah. Yeah, optimizations too. We'll say good. Compilers, what is code generation? Yeah, so it's basically where you take the result of the semantic tree and you convert it to a control flow graph or some other intermediate representation. Good. Compilers, what are some of the basic ways a compiler optimizes code? Yeah, register allocation, assigning variables to hardware registers, and also taking advantage of more advanced CPU instructions in order to avoid branching and reduce the amount of times, or reduce the amount of work that the CPU has to do. Yep, register allocation, using more efficient CPU instructions to eliminate the need for branching. Good. What is meant by the back end of a compiler? Anything that is machine dependent. So like optimizing for specific hardwares. Compiling to specific assembly language, specific, what do you call them? CPU instructions that are, only used on certain hardware architectures. Yeah. So I wrote optimizing and translating for specific architectures. That's what I was trying to get at, but that's a much more succinct way of putting it. So optimizing and translating for specific architectures. So we'll just do that again. Compilers, what is the advantage of having the compiler output assembly language instead of machine language? One, assembly language is much more easier to debug. And it's a lot more easy to output to assembly than it is to output to machine languages, because with machine languages you have to do like specific architecture stuff. Yep, fairly easy. What does an assembler do? An assembler takes, in the context of like G++, it will take the assembly code and translate that into relocatable object code or relocatable machine code. Yep, pretty easy. What is the symbol table? So it's a data structure that's used in a lot of the different phases of compiling, and it stores references to tokens. It stores like the attributes of each token. It can store references to certain operations. It can also like differentiate between different classes of different types of tokens, different categories of tokens. Yeah, that's pretty much it. The mappings from the lexical analysis phase: tokens reference symbol table with columns and indexes, e.g. ID. 2. Yeah, that's... Not sure if that's super important to remember, this specific notation, because it's going to... I feel like that's probably going to be dependent on every different compiler's going to have a different way of doing it. So, yeah, like, I pretty much described what it was, but let's just, for the sake of this, we'll redo this one. A data structure that contains the mappings from the lexical analysis phase. We'll just do it again. I don't want to cheat here. What is semantic analysis? So it's the third step in compiling. It's where you take the output of the syntactic analysis, which is usually like an abstract syntax tree. You do type checking on it, and you check it for semantic correctness, as in like language correctness, and that it's actual valid program. Cool. That was. I'm gonna say good. What is a symbol table? So the symbol table is a data structure that contains the output from the mappings from the lexical analysis phase, where you map the token to an entry in the table along with its attributes, like for example ID and 2. Yeah, good. Compilers, what is meant by the front end of a compiler? Anything that's not machine dependent. So the optimization phase, lexical analysis, semantic analysis, syntactic analysis, etc. Anything that's can be generalized. Compilers, what are some basic ways a compiler optimizes code? Number one, register allocation, allocating variables to hardware registers, and taking advantage of more advanced CPU instructions to avoid branching. What is code generation? It's where you take the results from semantic analysis and you convert it into some intermediate representation like a control flow graph, or a that's it. Good. What is meant by the back end of a compiler? Anything that's machine dependent. So optimizing and translating for the specific machine that you're on. Compilers, what is the symbol table? It's the data structure that contains the mappings from the lexical analysis phase. It contains, it maps the token to an entry in the table along with its attributes. For example, ID and 2. Good. Okay, done with that for today. We'll create a new deck for the lesson 2, which is lexical analysis. And regular expressions. All right, sync that. Okay. Lesson 2, lexical analysis and regular expressions. Tokens. The first step of a compiler is lexing, aka scanning or tokenizing. The goal is to break up an input stream into tokens. For example, given the input stream containing the characters simple code, if B equals 0, A equals high. A natural tokenization would be if bracket b equals 0 bracket a equals a string literal high, where the vertical lines indicate token boundaries. Token typically fall into certain recognizable classes such as identifiers. Makes sense. Keywords. Yep, so keywords of the language makes sense. Literal constants. Yep, and operators. Most lexers discard whitespace and comments since these are not needed by later stages of the compilers. An exception would be a parser for a system like JavaDoc that generates documentation from contents of appropriately placed comments. If we were going to write a Java type signature for a lexer, it might be a function that accepts a reader and returns an iterator of tokens. Make sense? That the signature should also have some provision for reporting lexical errors when the input stream cannot be broken up into legal tokens. Many tokens contain useful information. For example, an integer literal contains the actual integer. Right. That's true, it does. These are called token attributes. Yeah. In a language like Java, it would be natural to represent tokens as objects whose token attributes are arguments to a constructor. Thus, we might represent an identifier A as an object new identifier A, a floating point literal 10 as new number 10.0, or string literal hello as new stringlet hello. Notice that in the case of the string literal, the input for the token contains 7 characters, whereas the token attribute has already been interpreted as the corresponding 6-character string. Notice that the case of the string literal, the input for the token contains 7 characters, whereas the token attribute has already been interpreted as the corresponding. Right. So yeah, I guess you have to escape. You have to escape string literals and think about that. In addition to the information content of the token, we usually want additional information in each token. Its position in the input. Yeah, that's cool. Makes sense. This position would often be described by the name of the input file, the line in that file, and the column in that file. Okay. So that's how they do it. They store all this stuff in the symbol table. Makes sense. This position information is used later in later compiler stages if the compiler needs to report the location of an error. Ad hoc lexing. Actually, is there anything that we really need to remember here? Not specifically, no. Like that's all fairly makes sense really. What is ad hoc lexing? It's good to have a principled way to build lexes. Often programmers are too impatient and end up writing lexing code by hand. This approach turns out to be surprisingly error prone, leads to a large fraction of security vulnerabilities in real systems, particularly when programmers write their lexes in unsafe language like C and try to make them as fast as possible. One challenge of lexing is that tokens can overlap. The lexer can't tell, for example, if it is seeing a keyword or a variable identifier until it has read multiple characters. Tokens can overlap. The lexer can't tell, for example, if it is seeing a keyword or a variable identifier until it has read multiple characters. Okay, so if you name your variable, like, it's too yellow. This var, it's going through, iterating through, and when it gets to this, it may see that as like the keyword this. I guess it has to peek ahead to make sure that that's not the end of the string. Make sense? A second challenge is that the Lexa typically needs to look ahead, beyond the current token in order to decide where the token ends. Unfortunately, the standard I/O interfaces typically don't support this look ahead. Okay, for example, we might think that we could write Java code to scan an identifier like the following, assuming an appropriate method is ID char. Okay, so we have input file, while true, int c, input.read. If it's not an ID char, break out of the loop. If it is, append it to some ID variable. Do you see the problem with this code? I'm going to try not to cheat. Do we see the problem with this code? Well, true. Input.read. Well, yeah, it's the exact problem that I had outlined here. Like, yeah, so it's doing exactly that. It's moving forward. It's reading a character. If it gets to here, wait. If it's not an ID character, break. Okay. So if it gets to, so if it expects that this is some ID, like valid ID, that's some valid ID there. It iterates through. It gets to the next character. If that's not a valid part of the valid ID, then it's just going to discard it. Like, it's just going to... Yeah, it just breaks and just discards that, whatever this is. Just gets rid of it, I guess. Like, because like the next call will be... yeah, I don't know. Let's continue. It reads and discards the character just after the identifier. Yeah, this might not be a problem if the character is white space. In general, the discarded character will be part of the next token in the input stream. Right, yeah, because if you have like a bracket afterwards, the bracket may be super important for doing a mathematical calculation. And if you get to it and you realize, oh, okay, we're at this bracket which is not in our valid ID, we're just gonna discard that completely, then you'll be missing out on potentially semantic, like information that is semantically important. I'm assuming that's what they're getting at. In general, the discarded character will be part of the next token in the input stream. The solution to this problem is to use a richer abstraction for reading input, one that allows client code to peek at the look-ahead character. Then the code to scan and identify can be written correctly and simply along the following lines. While the next character is valid ID char, append the append the next character. Look ahead doesn't solve the problem with overlapping tokens though, unless the input source also supports backtracking. For an example of an input source that supports both look-ahead and arbitrary backtracking, see the scanner class in the Easy.io package. That's a GitHub link. A replacement for the Java scanner class, originally developed for Cornell CS4120. Source Easy.io. What are we looking for? Backtrack scanner? Just scanner. See the scanner class. Can I zoom in on this? So the scanner extends back. Yeah, extends the backtrack scanner. Constructor. Scan past any white space. Here we go. Next digit. Peaks. Character is digit. Advanced. Okay. Scan past all digits at the current position, if any. Next digit. Yeah. Peak. Do we have previous digit? Have some sort of like, yeah, previous digit back. Digits, scans one or more digits. Cool. Probably gonna get off track here, so let's keep going. Regular expressions. Actually before that. Alright, is there anything that needs to be remembered here? Well, not 100% because it's sort of saying that this is not the way to do lexing, because you're not going to solve the problem of overlapping tokens, even if you do solve the problem of discarding required tokens. So I'm guessing it's leading up to something. Regular expressions, here we go. A more declarative approach to lexing is to define the legal tokens using regular expressions, and then to automatically synthesize the lexer from these regular expressions. How do you automatically synthesize the lexer? I guess we'll find out. This approach is easy and is more likely to result in efficient, maintainable, secure code. Tokens in programming languages can be quite complex, so regular expressions need to be expressive. For example, C and Java support floating point literals like 2.0.1E0, 20.E99. How do we compactly represent and efficiently recognize the legal floating point literals? A regular expression R denotes a set of strings called the language of R. Written, language of R. Using the regular expression language that is commonly used for lexer generators, we can define the language recognized by various common regular expression constructs. So I don't know regular expressions pretty much at all, so I guess we're about to do some learning. So, okay, so A, ordinary character. The language is a set containing the character A. Simple. So this represents the set containing just the empty string, so an empty language. R or S is the union. Okay, it's the union of the language R and the language S. Makes sense. Am I gonna need to remember this though? Not sure. Moving on. So RS is the set of XY where X is in the set, X is in the language of R and Y is in the language of S. I'm not sure what this specifically means. XY pipe. I don't know what that means. Does it mean XY where, or X, like X times Y, where X is in the set, well, X is in the language R and Y is in the language S. Oh, where do I find what that means? This is probably discrete mathematics, which is something that I haven't done in years, which I will get to. Oh, this has got to be like, yeah, discrete mathematics notation. How can I? You know what? I'm just gonna ask ChatGPT that question. Bear with me. The expression XY represents the concatenation of two languages typically used in formal language theory and theoretical computer science. Here's what each part of the expression means. So X and Y are placeholders for strings. It means X is a string that belongs to the language R, we knew that. The symbol represents the logical AND, we knew that. The expression represents the set of all possible strings X, Y, where X is from the language R and Y is from the language S. Yeah, okay, that makes sense. For example, if R is, and S is the language 01, then the set of all possible strings X, Y, where X is from the language, Y is from the language S, would represent the set of all possible combinations of strings R and S, such as, yeah, okay, all right. All right. Awesome. Asterisk is the union of the empty language and the language of R and the language of R, which is, what does that mean? I have no clue what that means. I'm going to have to ask ChatGPT again. Yep, so renew what that means. Represents the LRR represents the language formed by concatenating two instances of R. Represents the language formed by concatenating three instances of R. Okay. Don't know why you need to do that, but I guess we're going to find out. Yeah, so if a set would include things like A, B, A, B. Cool. All right. Continuing on. Assuming A and B are ordinary characters from the alphabet we're using to make tokens, here are some examples of regular expressions and the corresponding language. So the set of all possible strings such that A is in language, well, A is in this set and the empty set is just A, whereas the union between A and B is just the set containing A and B. A, B, I'm not sure what that means. Is that like prime or something? Does that mean AB prime? Is the union of the empty set, then A and B, well, the language of A and B, the language of A and B concatenated with the language of A and B, on so on and so forth. So this one says the union. Wait. The union of A and the empty set concatenated? I don't know the lingo. Okay. Okay, I don't understand that last one. So we have the union of A in the empty set is just A. So that just becomes A. Yeah, I completely don't understand that last one. Asking ChatGPT. The regular expression A union empty set times B, I guess it's times, I'm not sure, represents a pattern that matches two strings, A, B, and B. Let's break down the components. So the union of A and the empty set is part of the regular expression, specifies that you can match either A or the empty string epsilon. In regular expressions, the vertical bar is used as an alternation operator, indicating a choice between multiple options. B is the literal B character. Now let's see how this regular expression matches the strings. AB in this case, A union epsilon matches A, and then B matches the B character, right? So the entire regular expression matches AB. B in this case, A union epsilon matches the empty string epsilon, And then, okay, B matches the B character. Okay, so the entire expression matches B. As a result, the regular expression A union epsilon B matches both A, B, and B, which is why the set of strings attached to this regular expression is A, B, B. I'm probably going to... I'll finish off this little section and then I'll figure out what's going on. Using these basic regular expression constructs, we can define convenient notations for describing the tokens in programming languages as syntactic sugar. We can define convenient notations for describing the tokens in programming languages as syntactic sugar. R question mark is the union of R and epsilon. R plus is R times R, essentially. I still can't, my brain's not making the connection between oh, okay. So I don't understand what R like times R asterisk R would be, but like that makes sense. As in, this is just syntactic sugar for yep, R, the union between R and the empty set or the empty string. So in brackets ABC, A or B. So it's a regular expression that matches A, or the union between A, B, and C. This is known as a character class. This, I guess that symbol means like negating or something. Any character except A or B. Regular expression A to Z, any alphabetic character, that makes sense. Any non-alphabetic character, because you're negating it there, makes sense. ASCII 10 new line character. So I guess that's just some sort of, yeah, I guess it's just how you detect new line characters. Fair enough. Dot is anything but a new line character. Roughly negate, right, so yeah, the negation of new line character, ignoring Unicode new line characters. And just the negation operator is any character, or the brackets negation operator. Whew, okay. How much of this am I gonna need to remember? So A, B prime, or whatever that is, asterisk, is equal to empty string, AB, AB, AB. So that one makes sense. So the union of A and B is equal to, so the union of A and the empty string is equal to the union of this and this, which is just this. No, it's not. That's wrong. I'm completely wrong. It's um, let me draw that out. A union epsilon is equal to A and the empty string. Yep, that makes more sense. I don't know if memorizing this is needed. This may just be something that I need to reference in the future. I may regret not memorizing this, but I'm just going to move forward and see. Yeah, see, I can always circle back to this if I need it. So, Lexa generators. A Lexa generator like JFlex, Lex, or Camel Lex takes as input a specification consisting of a set of regular expressions specifying the various legal tokens. JFlex, Lex, or Camel Lex. Let's look that up. Lex. Lex software. Lex is a computer program that generates lexical analysis. Lex is commonly used with the Yak parser generator. Lex, originally written by Mike Lesk and Eric Schmidt, and described in 1975, is a standard lexical analyzer generator on many Unix systems, and an equivalent tool is specified as part of the POSIX standard. Lex reads an input stream specifying the lexical analyzer and writes source code which implements the lexical analyzer. No way. That's insane. So if I go man Lex, holy shit, Flex, the fast lexical analyzer generator, generates programs that perform pattern matching on text. Change. Have any examples? No way, you can generate C++. The full documentation for Flex is maintained as a text info manual. If the info on Flex programs are properly installed at your site, the command info flex should give you access to the complete menu. I have no idea. Huh. Tool for generating programs that perform pattern matching on text. This edition of the Flex manual documents Flex version 2.6. Simple examples. First, some simple examples to get the flavor of how one uses Flex. Following Flex input specifies a scanner which, when it encounters the string username, will replace it with the user's login name. Username printf. Cool. By default, any text not matched by a Flex scanner is copied to the output. So the net effect of this scanner is to copy its input file to its output with each occurrence of username expanded. In this input, there is just one rule. Username is the pattern and the printf is the action. The symbol marks the beginning of the rules. Here's another simple example. And num lines equals 0, numchar, so the rules start here. So it looks like for any new line, we increment number of lines and number of characters. And for any dot, we increment number of characters. Or for any, I guess dot means any. Oh no, that's true. Dot means any character. Is that right? Let me check. Anything but new line character. Cool. Yeah, and then it just spits out the number of lines and characters. This scanner counts the number of characters and the number of lines in its input. It produces no output other than the final report on the character and line counts. The first line declares two globals. Number of lines. Yep. Somewhat more complicated example. Okay, here we go. We got some big boy stuff happening here. So we have a rule here. I guess it's just including it. Oh no, that's not a rule. Not sure what that is. Some comment, I guess. Okay. So the rules start here, I guess. For any digit, prints out an integer. Digit plus any of these keywords. Then it prints out the keyword. If an ID is found, it prints out an identifier. If any of the operators are found, it prints out an operator. Eats up one line comments. So I guess ignores one line comments. Eat up white space. So it ignores space, it ignores a tab, and ignores new lines. And I guess if it finds anything else, it prints unrecognized character. This is the beginnings of a simple where am I? This is the beginnings of a simple scanner for a language like Pascal. It identifies different types of tokens and reports on what it has seen. The details of this example will be explained in the following sections. Flex input file consists of 3 sections separated by a line containing only these characters, definitions, rules, user code. Yep. Okay, well, this is really cool, but I'm not going to dive into the details of this this program just yet. Okay, Alexa generator like JFlex, Lex, or CamelX takes as input a specification. It outputs code implementing Alexa that breaks its input into tokens. In the Alexa generator spec, along with each token is an action that Alexa performs, and the token is matched against the regular expression. That is so cool. For example, the action might be to turn an object representing the matched token, or simply the action might be to return an object representing the matched token, or simply to do nothing, ignoring the matched input. And we did see that in did I lose the... Yeah, I lost that. Yeah, so here it's just eating it up, as in eat up means do nothing. Here we're printing stuff. Printing. Here we define what a digit is, and we define what an ID is. That makes sense. Very cool, Kanye. To aid in writing lexical specification, a Lexa generator like JFlex also supports defining abbreviations, which can be very helpful for building up complex regular expressions. Once defined, an abbreviation can be used to define regular expressions, including in other abbreviations, as in the following. So digit is 0 to 9, pos int is 1 to 9, a digit that is 1 to 9, I'm guessing. Keep in mind that abbreviations cannot be recursive. A definition like x equals set of x, a union epsilon is illegal because it cannot be fully expanded. Not to mention that it doesn't add anything above the definition. X equals a asterisk. Recursive abbreviations would give us the full power of context-free grammars, which is overkill for specifying lexical analysis. Recursive abbreviations would give us the full power of context-free grammars, which is overkill for specifying lexical analysis. Okay. The following JFlex example is a good starting point for writing a JFlex spec. So at the top, we're defining we're creating definitions. What? Above, not in notes. Okay, so yeah, we define what white space is, we define what a letter is. Digit identifier is any letter times the union of digits and letters. And I guess this underscore, and it's any, what was that again? It was like any combination of them, yeah. This is totally another language. An integer is a union of 0, hyphen, what does that mean again? What does question mark mean? The union of some set and the empty string. 1 to 9. I literally don't understand this. Any combination of that. 0. Gonna ask ChatGPT what this means. Represents a pattern that can match two types of strings. O. This part of the regular expression, single character O. This part of the regular expression is more complex and matches numbers that are not 0. Here's a breakdown of this. Yes, so the question mark. This part matches an optional hyphen character. The question mark makes the hyphen optional, so it can be present or absent. This matches a single digit from 1 to 9. Yep. Ensures the number doesn't start with leading 0. Okay. Digit. This part represents a digit repeated 0 or more times. Okay? It allows for any number of digits following the initial digit. Right. Okay. Putting it all together, this part of the regular expression matches non-zero integers that can have an optional leading hyphen. Okay. Here are some examples of strings that this part can match. 1, minus 1, 2, 3, etc. This does not match because it's just 0, and the first part of the expression 0 is an alternative match. So the entire regular expression matches strings that are either 0 or non-zero integers with an optional leading hyphen. I mean, I figured that's like what an integer is. I guess I just couldn't. This is hard to pass. Float is a digit, which is 0 to 9, plus dot plus digit. And what does the plus mean again? R times R prime, or whatever that means, R asterisk. So any combination of digits, right? So any combination of digits, then a dot, then any combination of digits. Then here, what are we doing here? If we find a white space, we ignore it. If we find this identifier if, return new token, token type if. If we find some identifier, return new token with its ID and its YY text. What is YY text? Is that a Java thing? Standard input. Okay. Wait, what? Standard input, standard output. The goal of Lex is generate code for a C function named yylex. This function is called with no arguments. It returns an integer value. Value of 0 is returned when end of file is reached. Otherwise, yylex returns a value indicating what kind of token was found. Lex also creates two important external data objects, a string named yytext. This string contains a sequence of characters making up a single input token. The token is read from the stream yin, which by default is the standard input. An integer variable named yyLength. In most Lex programs, a token in yytext has an associated value that must be calculated and passed on to the supporting program. So, identifier, return new token, token type.id with its text, I guess the text of the identifier. Integer, return new token. Yep. So then we just pass the value, or the text, turn into an integer. Same thing with when we find a float, we just pass the float. Return new token. So if we find specifically the dot character, we return the new token containing the dot type. For certain token classes such as strings and comments, it is handy to make use of Lexa states, in which the recognized tokens differ. Lexa states in which the recognized tokens differ. We can modify the previous JFlex example to support comments by introducing a comment state to simplify scanning documents. The initial state of the lexer is yy initial. The function yy begin can be used to change the state of the lexer in an action. Regular expressions associated with a particular lexer state are only active when the lexer is in that state. State comment. YY initial. So that's the initial state. YY begin. The function YY begin can be used to change the state of the lexer in an action. So when we find this, the comment string, we change this lexer state into a comment state. We do a little console log sort of thing. And then when we're in the comment state, when we find the end of the comment string, we switch back to the initial YY initial state, do a little console log. While we're in comment, if we find any character at all, we just ignore it, do a console log. Okay, that makes sense. And that's the end. All right. Okay. Now I'm trying to decide how much of this is crucial to remember. Assuming A and B are ordinary characters from the alphabet we are using to make tokens, here are some examples of row expressions in the corresponding language. Oh man, I don't know. Well, I guess I eventually did plan on learning regular expressions one day, so may as well just start here, I guess. Just want to check What would happen if you try to match A, the union of A and empty string? What does the set look like? So it'll match, yeah, so it'll match either A or the empty string. That makes sense. Okay, I suppose it's time to start memorizing some regular expressions. I'm just gonna jump right in. AE, and that represents the set containing A. So it contains the set containing X and Y, all possible combinations of X and Y, such that X is in the language R and Y is in the language S. All possible combinations of X and Y, such that X is in the language R, Y is in the language S. Which means it's just A. Bridge X. What does this mean? What does this match? A or B? The union of the set A and B. Okay, so AB prime, that's like kind of a step up. So I'm going to say what regex will start more simple. What does this match? R prime. That matches set containing empty string etc. So what does this match? What does AB match? The set containing empty string. AB, etc. What else was there? There was okay, yeah, so the notation. What does this match? Epsilon aka the set containing R and the empty string. Regex, what does this match? ABC. Just matches the set A or B or C. Fairly simple. Regex, what does this match? ABC. Anything but or any characters but A, B, or C. Regex, what does this match? So I'm not going to need to remember like all of these, but it's just for me to get a basic idea of what I'm seeing. So the other two that I want to remember are probably the dot character, anything but a new line character. Because I'm probably going to see that a lot. And the last one there, the any character is something that I'll probably see a lot as well. And in 4 weeks' time, if these are not useful at all to me, I can just delete them. No skin off my back. Cool. Cool. And I probably want to remember what a Lexa generator is doing. Takes input as a specification consisting of a set of regular expressions. What is a Lexa generator? Takes a regex specification and outputs code implementing a Lexa that breaks its input into tokens. That is insanely cool. That is insanely cool. I can't wait to start using that. I'm going to mess around with that for sure. Okay. That should do us for this lesson. Thanks for watching, and our next step is going to be back. Our next step will be, I think we need to, so reading the Dragon book, chapter 3 to 3.3. So stick around for that.